All right, welcome back. Today we're totally shifting how you look at massive coastal infrastructure projects. We're diving into Japan's 400-kilometer Tsunami Shield. It's a $12 billion project that completely redefines how humanity pushes back against the ocean. We're going to strip away the concrete you can see on the surface and plunge deep underground to uncover the absolute marvels of engineering that actually make this possible. So get ready, because this is going to be incredibly fascinating.
So it's the ultimate engineering challenge, right? How exactly do you build a wall to stop the literal unstoppable? Well, to answer that, we've got to bust a major myth about the devastating 2011 tsunami. See, most of us picture the ocean simply smashing into these seawalls from the front and just breaking them like glass. But actually, scratch that. That's not what happened at all. The walls were designed for 8-meter waves, but the ocean swelled to 12, sometimes even 15 meters. The waves didn't just push through the walls, they topped them. And that overtopping triggered a totally different, much more insidious kind of mechanical failure.
Okay, let's dive into this. The real culprit wasn't actually the wave arriving, it was the wave retreating. This is a phenomenon known as scour, or backwash erosion. When those massive volumes of water poured over the tops of the defenses, the real damage happened on the landward side, the back of the wall. This long-period inundation, combined with the really high-velocity return flow of the water, aggressively stripped away the foundation material that was supporting the base of the structures.
And looking right here brilliantly illustrates exactly how that failure occurs. As the overtopping water crashes down, it basically acts like a massive waterfall, violently hollowing out the earth at the rear toe of the foundation. And once that earth is gone, well, the wall has absolutely nothing to lean on. The entire massive concrete structure literally loses its footing and tips over backward. That was the primary failure mode in 2011. So when engineers set out to rebuild, they quickly realized they couldn't just build taller walls. They had to rethink the foundation from the ground down.
Which brings us to Section 1, the subsurface reality.
So, that towering 4-story concrete structure you see along the coast? That is literally just the tip of the iceberg. Constructing the hidden foundation beneath it is this incredibly delicate process, actually monitored entirely by sonar. First, an uncompacted rubble mound is built up from the ocean floor with these exact 1 to 1.5 slope angles. Next comes a really crucial component, a geotextile membrane. This synthetic fabric acts as a filter layer. It works silently down there forever, allowing water to pass through but stopping fine soil particles from migrating and bleeding away into the voids of the rubble. Finally, massive steel sheet piles with interlocking Z-profiles are driven a staggering 10 meters deep into the ocean floor, simply to protect the toe of the wall from that devastating backwash scour we just talked about.
Now you might be wondering, why go through all this immense trouble underwater? 2 words: hydrostatic pressure. This is the massive, accumulating horizontal force of a moving body of water. A tsunami isn't just a surface splash, It's a deep, incredibly powerful column of water displacing immense energy. If a wall isn't anchored deep enough, the sheer horizontal push of that hydrostatic pressure is going to cause the entire structure to slide or overturn. That buried foundation has to be strong enough to resist the entire ocean pushing against it.
And this beautifully visualizes that subsurface reality. Just look at the sheer scale here. Notice how the mound foundation and stabilizing elements extend far below the visible crest. To put it in perspective, while the visible wall might stand, say, 14 meters high, the foundation piles can be driven a staggering 25 meters deep. This really proves that the real fight against the ocean doesn't happen up in the air. It happens down in the dark, submerged layers. The concrete you see up top is just the final barrier. The earth and steel below are what actually hold the line.
All right, moving on to Section 2, armoring the coastline.
Now what's really interesting about this is, even with a deep foundation, you can't just let the ocean smack into a flat concrete surface. You have to break the wave's energy first using tetrapods. These are massive 4-legged concrete structures. But here's the absolute genius part. They are not placed precisely, they're dropped. They're allowed to find their own stable position. It's essentially chaos creating order. The interlocking gaps between these tetrapods aren't a weakness, they're the exact mechanism designed to absorb and dissipate the force of millions of tons of rushing water. Engineers actually use a complex formula called the Van der Meer equation to calculate the exact minimum armor weight they need based on incoming wave energy. Oh, and at the very top of the main wall, there's a special crown wall nose, shaped specifically to deflect overtopping water right back out to sea.
Which leads us perfectly into Section 3, Level 1 versus Level 2 disasters.
So what exact size of disaster are these engineers actually planning for here? Are they trying to build an invincible magic shield against a literal apocalypse? Not quite. The authorities have implemented a 2-level tsunami hazard classification, and understanding this is absolutely crucial to getting the engineering philosophy. Level 1 tsunamis are higher frequency events, happening maybe every 50 to 160 years, generating waves around 7 to 10 meters high. The wall is designed to completely block these. Level 2 tsunamis, on the other hand, are rare monsters. We're talking every few hundred to a few thousand years, generating waves well over 10 meters. The shield is actually not expected to block a Level 2 event. It's engineered to survive it without structural failure.
As you can see, in a Level 1 scenario, the coastal defense structures act as an absolute barrier. The wave rolls in, hits the armoring, and the wall just stands tall, keeping the entire community behind it completely dry and protecting their property. It's a practical tool for the most probable disasters, and it handles them easily.
But, and this brilliantly illustrates the difference, a Level 2 scenario is a whole different beast. The wave exceeds the height of the wall. It overtops. The community behind it will flood. But because of those geotextile membranes, the deep 25-meter sheet piles, and the scour protection we talked about earlier, the wall doesn't tip backward. It maintains its structural integrity. It slows the water down and completely prevents a catastrophic dam break effect that would release an even more intense, deadly torrent.
Okay, let's look at Section 4, Green and Gray Infrastructure.
Because, let's be real, building 400 kilometers of sheer concrete walls, some nearly 4 stories high, can feel a bit like living in a prison for the locals. It definitely impacts tourism and local culture. So to combat this, projects like the Marino Project are proposing something amazing: tsunami mitigation parks. They're integrating green and gray infrastructure. So instead of just a massive concrete face, engineers are combining traditional gray concrete breakwaters with green elements. Think deep-rooted forests and elevated natural earth berms. These dense tree lines act as a natural net. They weaken the power of the tsunami waves naturally and stop heavy destructive debris from rushing inland, all while keeping the coastline looking beautiful.
Finally, let's hit Section 5, Managing, not eliminating risk.
As we wrap up this explainer, we really have to look at the big philosophical takeaway here, because no matter how much concrete you pour, the ocean is always going to be more powerful. Here's a pro tip for you. In traditional construction, your goal is usually to eliminate risk entirely, but in coastal engineering, you only manage risk. You just have to accept that you cannot stop nature. The interlocking tetrapods, the incredibly deep foundation scour protection, the green mitigation parks, they are all just part of an intricate multi-billion-dollar delay tactic. You're engineering the ultimate safety buffer to reduce the wave's energy and just buy the community precious time to reach high ground.
Which brings us to a pretty provocative thought. We can design smart walls that bond directly to basalt cliffs. We can lay high-tech geotextile fabrics, and we can engineer foundations to survive Level 2 overtopping events. But the final variable? It isn't concrete or steel. It's human readiness. We've engineered the ultimate safety buffer, but are we actually prepared to run when that ultimate wave arrives? The infrastructure can only buy us time. It's entirely up to us to use it.
And that wraps up our deep dive into the iceberg engineering of Japan's massive seawalls. But before you go, I want to hear from you. What should we unpack next time? Should we look into the lightning-fast mechanics of automated floodgate engineering, like how they close in literal seconds? Or should we dive into the incredible computer physics behind tsunami wave modeling? Let me know. Keep learning, and I'll see you in the next explainer.